In the last video, I showed you how we obtain the concept of stress tensor from the traction, the following courses approach using a tetrahedron. Today, I'd like to extend that consideration to obtain the concept of internal energy and the strain tensor. The motivation is given here. So we write, so if you consider the work conservation, usually we write the external work is equal to the internal work. That's how we write. And especially we write internal work. The internal work is work done by the stress tensor over the strain tensor. So if you consider variation, we put the variation operator delta here, and then this is the variation operator put in front of the work sign. So how we obtain, the question is how we obtain the form of the definition of internal work using the stress tensor and then the strain tensor. So are we able to derive the form of equation from the consideration of the work or calculation using the traction and displacement that we can observe from the surface of structure rather than stress tensor, stress state? Okay, so let's consider a material point here. Let's say we have a structure subjected to different loading conditions. It can be distributed at some point, it can be the moment, and then also we can consider the body force too. Then we can imagine we have a material point. So once we have material point, this material point can be considered further here for further discussion. Let's say I have material point. And then if you read this material point in that direction with respect to this normal, then we may have certain traction. And then also this traction depends on how we read the stress state. If you consider this normal, then we must have another traction. So traction depending on the observation direction. So if you project the stress state into another body, let's consider a circular section here, and then I want to consider many material points, the stress state of which are exactly the same stress state. That's why it's in equilibrium. But from the surface, there must exist the traction to keep the equilibrium. Okay, then along the surface, we can calculate the work done by the traction. Say I have traction, and then if you consider the variation of displacement over the surface, then we can imagine this kind of displacement variation, delta U. And then my traction must do work over this displacement variation. This is the work done by traction over displacement variation. Then we can understand that this quantity is the work done by the traction over the displacement variation. So let's consider Corsi's definition. The Corsi's definition is the traction can be represented by the stress state tensor sigma. So make sure that here sigma is two-dimensional matrix, sigma ij. Instead of, in the case of three-dimensional problem, so I is from 1 to 3. And then n is normal traction. So this is how we represent traction. Make sure the traction is a vector here. Then the work done by traction can be written by the stress sigma ij and the normal nj, dot product between the stress tensor and normal, and then delta ui. This is the work done by traction. So let's take a look at this equation carefully. I have normal, and then the integration is for a surface. Then maybe you can remind the so-called divergence theorem. Yes. So we can consider divergence theorem. So divergence theorem is So if you have integration for a quantity with the normal vector, and for example J and dA, that can be transformed to corresponding volume integration. Here the integrand becomes a differentiate derivative with respect to coordinate, and then it becomes the volume integration. So this is integrand in the surface integration is given by this. And that's why instead of writing this, so we consider the differentiation with respect to coordinate. So now we have two terms, stress tensor and then displacement variation. That's why we have two different terms. So here, if you look at the first term is equilibrium condition. If we don't have body force, what I mean body force is equal to 0 in the continuum version. If my continuum is in equilibrium, the derivative of stress tensor with respect to coordinate should be equal to 0. But what if body force is not equal to 0, like gravity or magnetic force, we have non-zero body force, then it should be, we need to have extra terms. Here Bi is the body force. Okay, so this is what I'm saying. This is the equilibrium equation. So for the continuum version of equilibrium equation, I have another video. Check out the video for actual derivation of that form of equilibrium, or you can refer to my class lecture note for my finite element course. So substituting that information into the work done by traction is given by this equation. And then make sure that the body here, I have many material points. And then if you look at the surface, I have traction. And then I want to consider non-zero body force too. That's why the external work should be given by the work done by traction and the work done by the body force. So let's plug in work done by traction here. Then we can easily recognize that the work done by the body force is cancelled by each other. But finally, external virtual work is represented by integration stress tensor. I have another tensor del u I comma j. So naturally, because of work conservation, we can understand that this is the internal virtual work. So as you understand, the sigma ij is what is measured for the internal stress state. Now let's take a look at the derivative of displacement variation with respect to coordinate further. So make sure that if we have any square matrix, the square matrix can be represented by its symmetric term and then its anti-symmetric term for any kinds of square matrix. The similar to this, so we can write this u I comma j. So I told you that I and j are representing the indices. That means the del u I comma j can be represented by 3 by 3 matrix, the square matrix. That's why we can consider it's a symmetric part and then the anti-symmetric part. So here the symmetric part is, to represent the symmetric part, is nothing but we can write, we can interchange I and j each other, and this is the anti-symmetric part. So now instead of plus sign, and to represent anti-symmetric part, I have minus sign here. So look at that. Here the stress tensor is symmetric. Sigma ij is equal to sigma ji. So if you count sigma ij delta epsilon ij plus delta omega ij. Omega ij is anti-symmetric, but here now I want to look at sigma ij delta omega ij. Then from this expression, definition of delta omega ij, this is equal to a half sigma ij delta u I comma j minus a half sigma ij delta u j comma I. So look at this. And then because sigma ij is symmetric, that means we can write, instead of ij, we can write ji. And then here j and j, they are repeating index, and I is also repeating index. That means we can interchange the two indices each other. Then the first term and second term, they are cancelled. So no contribution by the second term. So finally, my internal virtual work is given by a quantity, stress tensor, and then double contraction and this term. Here we want to define epsilon ij, the symmetric part of the displacement derivation with respect to coordinate. Then we can define this is strain tensor. That's how we define strain tensor. The strain tensor is the counterpart of stress tensor in the sense of energy. So I'm talking about here. So energy conjugate to traction is displacement, and the energy conjugate to stress is strain. This is the physical meaning of this diagram. Okay, further, if you replace here the delta variation by d, then we can define the incremental internal work density, the stress sigma ij, and then d epsilon ij. The integration of this incremental internal work becomes internal work. And then in the case of elasticity, if you plug the modulus tensor and then strain tensor, then we can obtain the final form of the elastic deformation energy. So let's extend that approach to the finite deformation. In the case of finite deformation, say initially I have, before deformation, let's say I have omega naught. And then if you increase the further the stress level, and or if you have certain history of loading, then my initial domain would deform like this in different times. So omega t1, and then also the omega t2, blah 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 blah. Okay, so displacement is not fixed; it's evolving by the time. That's why in this case, instead of using the work, so let's consider the power. The power is change of work over the time. That's why now we consider the work, the traction, the work done by the traction over the velocity, and that is the power. The similar to the last time, we calculate the power over the surface of deformed body, and then I want to replace the traction by the Cauchy's definition stress and the normal. Then finally, if you use the divergence theorem, the surface integration can be changed by can be transformed to the volume integration using the divergence theorem. So similar to last time, so I have the gradient of velocity, and this is called velocity gradient tensor. So again, and then again the velocity gradient tensor can be decomposed to rate of deformation, and then the spin tensor. The name is rate of deformation and the spin tensor. So again, similar to last time, the rate of deformation is nothing but the velocity, the symmetric part of velocity gradient, and then this is anti-symmetric part of velocity deformation. So because the stress is symmetric, that's why the contribution of the spin tensor to the work is equal to 0. Finally, we can obtain the form of power. The internal power should be given by the stress tensor and the rate of deformation. And that is, in a dynamic problem, the counterpart of strain. The stress and then the rate of deformation. So let's formulate the same thing with respect to reference configuration. Here we talked about the initial configuration and then the deformed configuration. what we discussed is for the deformed configuration. Now let's consider the initial configuration. So if you follow, the starting point is this, starting from this equation. So if you transform, if you consider transform equation between the Cauchy stress tensor and the nominal stress tensor, or the deformation gradient, for the transformation referred to continuum mechanics textbook, the same energy, same power can be formulated using the nominal stress measured in reference configuration, and then the rate of deformation gradient, and then make sure that that integration is for the initial configuration. And also, instead of using the rate of deformation gradient, so we can consider so-called Green-Lagrange strain, the large deformation. So if you do that, considering this energy conjugate, so we can use the form of so-called second Piola-Kirchhoff stress. Then this is a third form of the power equation. So finally, summarizing, for the small strain, the work done by traction over the surface can be transformed to the work done by stress tensor over the strain tensor. We can extend it to the large deformation, finite strain. So here we have to deal with the power, and then here the stress tensor and the rate of deformation. Here the traction, and then work done by traction over the velocity, that is the power. This is the deformed configuration, and every time we need to deal with different configuration. And then we can do the same thing with respect to reference configuration before deformation. So depending on the application, we can use the first Piola-Kirchhoff stress, what I'm so-called nominal stress, or the second Piola-Kirchhoff stress. In this case, we have second Piola-Kirchhoff stress is symmetric. That is the benefit of using that. Okay, this is what I prepared in this slide.